Hello and welcome to my science tutorials. In today's video, we want to look at a resistor-inductor series AC circuit, or what we normally just call RL series AC circuit. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. Without further ado, let's begin. So an R and L series AC circuit, this is just the type of circuit that contains an inductor and a resistor as the main component or the major component. So if we draw the circuit diagram for this particular circuit, we have a resistor which is connected to an inductor, and then they are all connected to an AC source in this way. So the voltage across the inductor is what we call VL, which is the inductive voltage. So the inductor is L, the resistor is R. The voltage across the inductor is what we call the inductive voltage, and then the voltage across the resistor is what we call the resistive voltage. Now we have the total current passing through this entire circuit. Since they are in series, the same current pass through all of them, and then the voltage over here supplied by the source of AC is what we are calling the applied voltage. Now the applied voltage is the phasor sum of VR and VL over here. I'm going to be explaining what the phasor sum means later on in the tutorial. Now in this circuit, the current lags the applied voltage by an angle between 0 to 90 degrees. So we are saying that if we draw the phasor diagram for this particular circuit, we are going to have something that looks like this. We are going to have our resistive voltage over here. We're going to have our inductive voltage along this line. And then we're going to have our applied voltage is somewhere in between the resistive voltage and then the inductive voltage. Now, the angle it makes with the resistive voltage or the horizontal component of this axis, that angle is what we are calling the phasor angle. So this is what we call the phasor diagram. This is the phasor diagram. And then over here, this is our applied voltage. This is our circuit diagram. Now, from this phasor diagram, if we extend this to complete the triangle that we have over here, we can make some deductions from this particular phasor diagram. So we can have something we call the voltage triangle and then the impedance triangle from this phasor diagram. So let's have a look at that. So the first one I want to look at is what we call the voltage triangle. And it looks exactly like what we have over here. We have the phasor angle over here. This is 90 degrees over here because it's a right angle triangle. And since we have the VL on the vertical axis over here, it corresponds to the length over here as well. So we have our VL over here, the inductive voltage, and then we have our resistive voltage VR on the horizontal axis, and then the applied voltage on the hypotenuse side of this. Now, the applied voltage is equal to IZ. The Z over here is what we call the impedance, which is the overall opposition to the flow of current in any AC circuit. The inductive voltage over here is the product of the current multiplied by the inductive resistance XL, and then VR, like indirect current, we know is equal to IR, which is current multiplied by the resistor. Right, so this is what we are calling the voltage triangle. Voltage triangle. Now, another triangle we can get is what we are calling the impedance triangle. So from the impedance triangle, it is still just the same, only that over here we are looking at the impedance or the opposition to the flow of current. So we know that over here is supposed to be the applied voltage, but instead of that, we're going to put Z, which is the impedance of the entire circuit. Over here, we know we are supposed to, on this axis, the vertical axis over here, we are supposed to put the inductive voltage, but we're going to put the inductive reactance over here, and over here we're going to put R over here. So this is what we are calling our impedance triangle. Impedance triangle. Okay, and then our phasor angle is over here. Now, from these two angles, the voltage triangle and then the impedance triangle, we can make some calculations. So let's have a look at what we can find from these two angles. Let me use a blue color for that. So using Pythagoras theorem, from this voltage triangle, if we want to find the applied voltage, which is the hypotenuse over here, that will be equal to V squared is equal to VR squared plus VL squared. If we make V the subject, we are going to have the square root of VR squared plus VL squared. And now this is what we are calling the phasor sum. Okay, the phasor sum of the resistive voltage and then the inductive voltage to get the applied voltage. So we said that the applied voltage can be obtained by the phasor sum of the resistive voltage and the inductive voltage. And then this is what we are calling the phasor sum. Phasor sum. Either this or what I gave earlier on over here. So this is how we find the applied voltage in this particular case. Now let's get some space and look at how we find the angle or the phase angle over here. So let me quickly erase the circuit diagram over here. All right, so if we erase, now that we have this space, let's look at how we find the phasor angle over here. Now we can see that in this type of circuit, we only have our inductive voltage and then the resistive voltage. So this is the opposite side of the triangle. This is the adjacent side of the triangle. So the trigonometric ratio that will give us opposite and adjacent is what we call tan. So we have tan, the angle, the phasor angle, to be equal to the opposite, which is VL, over the adjacent, which is VR. So it means if we want to find our phasor angle, we just need to find the tan inverse of the ratio VL over VR. So this is one important equation you need to keep in mind, and then this is another very important equation you also need to keep in mind. Now, if we look at the impedance triangle, we can also do something similar to that. To find our overall impedance for the circuit, Z is going to be equal to Z squared is equal to XL squared plus R squared. Okay, this is plus. And then to make Z a subject, we're going to have square root of XL squared plus R squared. It doesn't matter which of this you bring first, whether R or XL, you're still going to get the same answer. So this is the formula that we use. Question 3, this is the formula that we use to find the impedance of the entire circuit. So the impedance is the total or the overall opposition to the flow of current in an AC circuit containing two or more components, such as maybe an inductor, resistor, or a capacitor. Now, from the impedance triangle, again, we can also find the phasor angle. So that will also give us tan theta, or tan the phasor angle, to be equal to the opposite and then the adjacent. So the opposite is the inductive reactance over the adjacent, which is the resistance over here that we have. So to find this, we just find the tan inverse of XL over R. So this is another equation that is also very, very important for us to look at. Now, one final touch to find the, let's say, the current in the entire circuit. If you are asked to find that, we know V is equal to IR, okay, from Ohm's law. Now in an AC circuit, or in this particular example, we are looking at the applied voltage, which can be obtained by using the phasor sum of the resistive voltage and then the inductive voltage to be equal to the current, which is the same across all components. And then the opposition to the flow of current in this particular example is what we are calling the impedance, the Z over here. So it's IZ. Okay, and then we can find this Z by finding the square root of the inductive reactance squared plus the resistance squared. That is how we find the Z over here. So this is also another important formula that we'll be using along this tutorial. So equation number 1, equation number 2 or 4, 3 and 5, they are very, very important, and we are going to be using them in solving a lot of questions which will be coming very soon. All right, so now that we've covered the basics, let's look at some practical example or some problems and see how we apply these formulas or how we use them to solve questions. So problem number 1, we have in a series RL circuit, the potential difference across the resistor R is 12 volts and the potential difference across the inductor L is 5 volts. We are to find the supply voltage and the phase angle between the current and the voltage. So this is pretty easy. For us to enhance our understanding, let me draw this particular circuit. So we have a resistor R over here, and then we have an inductor L over here, and then this is connected to an AC source that has a voltage, applied voltage, this has a current, and then we are saying that the voltage across the resistor is 12 volts. So over here VR is equal to 12 volts, and then the voltage across the inductor, which is VL, is equal to 5 volts. All right, so now that we have this circuit diagram, we've been asked to find the supply voltage, which is the phasor sum of these two guys over here, and also find the phasor angle. That is, so if we draw the phasor diagram, we're going to have something that looks like this. We'll have our VR over here, and then we have our VL over here, and then our this V will be here, and this angle is what we are supposed to find. All right, so let's have a look at how we solve this problem. So the first thing we want to do is to code the formula of how to find the applied voltage. So to do that, we know V is equal to the square root of VR squared plus VL squared. Very easy, very straightforward. So we know V is equal to the root of our VR is 12 volts. So we have 12 squared plus our VL is 5. So we have 5 squared. So this is equal to, if we compute these into our calculator, we are going to get 13 volts as the answer for our supplied voltage. Now, the second part of this question is asking us to find the phase angle between the current and the voltage. To do that, we simply said tan the phase angle is equal to VL over VR, as we saw, or as we can derive from this particular diagram over here. This is opposite over adjacent, which is VR over here. We already know what our VL is. We already know what our VR is. So our angle is equal to the tan inverse of VL from the question is 5, and then VR from the question is 12. So our angle is, if we compute the tan inverse of the ratio 5 on 12, we are going to get 22.62 degrees. So this is how we solve a question involving an R and L circuit. Let's have a look at another example. Example number 2. A coil has a resistance 4 ohms and an inductance 9.55 millihenry. We are to calculate the reactance, which is the inductive reactance, the impedance, and the current taken from a 240 volt 50 hertz supply. We are also to determine the phase angle between the voltage and the current. All right, so this is very easy, very straightforward. Let's go ahead and write down our solution. So the first thing we want to do is to note the parameters that we have so that we know how we go around this calculation. So we've been told a coil has a resistance of 4 ohms. So our R is 4 ohms. It has an inductance L to be equal to 9.55 millihenry. So we are to calculate the impedance, the reactance, the current taken from a 240 volt. So we have our voltage to be 240 volts, applied voltage. We also have our frequency to be 50 hertz. All right. So the A aspect of this question is demanding that we find the reactance. The reactance in this case is the inductive reactance, which is XL. So XL, to find the inductive reactance of an inductor, it is given by the formula 2 pi FL. So this is equal to 2 pi. Our frequency is 50 hertz. Our L, the inductance, is 9.55 times 10 raised to the power -3. So if we compute everything over here into our calculator, we are going to get 3 ohms as our answer for the reactance. So let's go ahead and find B. The B is saying we should find the impedance. We know the impedance Z is equal to the square root of R squared plus XL squared. We just found XL to be 3, so that is a good news for us. So this is equal to our R, which is the resistance, is 4. So we have 4 squared plus our XL, which is the inductive reactance, is 3. So we have 3 squared. Now, if we compute everything over here into our calculator, we are going to get 5 ohms as the total opposition to the flow of current in this particular AC circuit. The C aspect of the question is demanding we find the current in this particular circuit. So we know voltage is equal to current multiplied by the impedance. This implies that our current is equal to the ratio of voltage to the impedance. And so this is also equal to, our current is equal to, our voltage is 240 volts, and then the impedance that we just found is 5 ohms. So our total current that passes through this particular circuit is going to be the ratio of 240 to 5, and that is going to give us 48 amperes. All right, so the final aspect of the question is asking us to find the phase angle. So this is very easy. So we know that our phase angle is tan. The phase angle is equal to either VL over VR, or we have XL over R. Now, because in this case we don't have the inductive voltage and then the resistive voltage, we are going to be using XL over R. So we know our tan, the phase angle, is XL over R, and the phase angle is tan inverse of our XL is 3 over here, our R resistance is 4 over here, and so our phase angle is going to be tan inverse of 3 on 4. That is going to give us 36.87 degrees. So this is our phase angle for this particular problem. Now let's have a look at one final example. We have a coil of inductance 318.3 millihenry and negligible resistance being connected in series to a 200 ohms resistor and a 240 volt 50 hertz supply. We are to calculate the inductive reactance of the coil, the impedance of the circuit, the current in the circuit, the potential difference across each component, and then the phase angle. So this is very easy. So let's go ahead and write down our solution. Now, for the sake of those who might not be able to visualize this, let me try and draw the circuit diagram. So the circuit, we have a resistor, we have an inductor, and then we have an AC source over here. So this is how our diagram is gonna be. Over here, we don't know the potential difference across each of the components. So VR and then the VL, we don't know. This is our resistor, this is our inductor L. The current I, we also don't know, but we know that the voltage is 240, and then we also have the frequency to be 50 hertz over here. We also know that the resistance is 200 ohms over here, and then the inductor is 318.3 millihenry. All right, so this is how our circuit diagram is going to look like. And then the first aspect of the question A is for us to find the inductive reactance, which is XL. And from the previous example that we did, we know that XL is equal to 2 pi FL. So with that in mind, we just write 2 pi FL, and we do the necessary substitutions. We know our frequency has been given to be 50. We have 50 here. And then our inductance is 318.3 times 10 raised to the power minus 3. Okay, so if we compute that into our calculator, we are going to get the value of XL to be equal to 100 ohms. Now, the second aspect of the question is asking us to find the impedance. We know that the impedance is equal to the square root of R squared plus XL squared. So this is equal to the square root of the resistance, we know is 200 ohms, so we square that, plus we just found the inductive reactance to be 100, so we have 100 squared. Now, if we compute that into our calculator, our impedance is going to have a value of 223.61 ohms. Okay, now let's continue to look at the third aspect of this question. We have to find the current flowing through this circuit. So we know that V is equal to IZ. This implies that our current is equal to the ratio of voltage to the impedance. And this is equal to, our voltage is 240 volts, so we have 240. Our resistance, which is the impedance that we just found, is 223.61. So let's divide that by, let's divide 240 by 223.61. So if we compute that into our calculator, it's going to give us a value of 1.073 amperes as our current flowing through the circuit. Now, the D aspect of the question is demanding that we find the potential difference across each component, which is VR and VL over here. So let's do that. So for VR, which is the potential difference across the resistor, is going to be IR. And we found the I, which is the current, to be 1.073 multiplied by the resistance of the resistor is 200 over here. So if we do the multiplication, we are going to get, for our VR, we are going to get 214.6 volts as our answer. Now, the second one is VL. So VL, which is the inductive voltage, is the product of the current and then the inductive reactance. Just as before, our current is still 1.073 multiplied by our inductive reactance, we saw earlier on, was 100 ohms that we found at the top over here. So we have 100 over here. And so if we multiply this by this, we are going to get 107.3 volts. Now, here is a catch for you to verify if your answer is correct. We said that the applied voltage is the phasor sum of these two voltages, so which is VR squared plus VL squared. Now we just found out that our VR is 214, so 214.6 squared plus 107.3 squared. Compute this into your calculator and see whether you get anything close or 240. If you get 240 or 239 point maybe 8 something something, then this should tell you that our calculations that we've done so far up until this point, everything is correct. So that is just a quick hack. So try it and see if the answer is correct. If it is equal to 240, it means you are right. But if it is not, then it means the calculation we've done over here is wrong. So let me know your answer in the comment section below. All right, let's proceed to find the last aspect of this question E, which is telling us to find the phase angle. So for the phase angle, we know tan the phase angle is equal to VL over VR. We just found these two guys, so we know this is equal to the tan inverse of our VL is 107.3, our VR is 214.6. So our phase angle is equal to the tan inverse of this ratio is going to give us 26.57 degrees. All right, so this is our phase angle, this is our inductive reactance, this is our impedance, this is our current, and these are our potential difference across the various components, that is the resistor and then the inductance. So thank you so much for watching, and I will see you in the next video. Bye bye.